Does anybody here identify as a physicist? One. Got a treat for you later. We've heard an awful lot about aqueous inks over the last couple of days. It's clearly a big push that the industry is making. The reasons, I think, are quite clear. Solvent inks have a great benefit. They dry very quickly. You don't have to do anything to it. It just happens naturally. But they can be harmful, in some cases even toxic. Aqueous inks, of course, they don't have any of those issues at all. But there's a bit of an elephant in the room that no one's really talked about here, and that's they take a very, very, very long time to dry. It's not unreasonable to expect 20, even 40 times slower than solvent-based inks. And this is an issue. When you go and, there's all these regulators out here, they keep pushing more regs onto the industry. We're all aware of things need to be food safe and so on and so on. But things are getting even more alarming when we look at some fairly common solvents such as MEK. The European Union is getting perilously close to declaring it reprotoxic, and that would put it into the category of materials of CRMs. And then if that ever happens, and it's looking close, the industry will probably need to change away from that kind of a solvent very, very fast. So I would look out for that. But the other thing is, of course, is that other solvents that you may often use, ethanol. There's quite a lot of restraints on exporting and importing ethanol. So if your inks are containing that, that causes an issue. And then, of course, the one thing that all businesses care about, cost. So there's some huge drivers for the industry taking us towards aqueous-based inks. And so what do we do about drying? Well, HP's here. They're great pioneers of thermal inkjet and water-based inks. They know about this. They've been doing it for donkey's years. Hot air. It's a very, very, very easy technology to implement. The capex is low, and you just throw enough hot air at it, and it should dry. But this is becoming even more important in the days of expensive energy. It's inefficient. You'd be quite lucky in some hot air systems to get 5% efficiency out of that. You can also damage delicate substrates, particular polymer films. It can be bulky, it can be noisy. I'm sure we've all been in plants with these giant corrugated printers, and the noise that comes off these things is huge. So hot air works, but not ideal. Now, we at 42T, we've been looking at this for a while, and we've looked at all the different ways that you might consider drying water-based inks. Broadband IR, that's been looked at these days quite a lot. You get quite a few good systems out of that. Some people think that this is the thing, this is the technology that's going to save us all. Only issue is that it's really not that efficient. You can go away and do some sums, and it's really only about 10, if you're lucky, 15% efficient. So there's an awful lot of energy that's doing nothing to dry your water. Narrowband IR, that's a really interesting technology. If you select the right LED, you can select the right wavelength, and almost all of that energy will be absorbed by the water. Looks fantastic. Only problem is, these LEDs might be £20, €20 per die, and that's far too expensive. Other heating methods, well, you can get your thinking caps on. Induction. Maybe if you're looking at metal substrates, you can think of induction heating, but that's not straightforward, and it's a very, very tiny market. And then there's the last one at the bottom here called dielectric heating. Well, we're all aware of microwaves. It's in everyone's kitchen these days. But they too are not very efficient because it's essentially a radiation process. So there's still tons and tons of energy that's not going to be absorbed by the water. And it's also not very easy to control. This is for the physicist out here, right? You're watching now. He's on his phone. I'm not trying to embarrass you, I promise you. There is another type of dielectric heating, which has been well known for quite a long time, but hasn't been adopted by the industry at all, and that's radio frequency drying. So for those of you who are interested in the science, this is what it's all about. If you get a bit squeamish about this sort of thing, because I keep being told, don't include any science in your talks, then look away now. Maybe your phone's your friend. Anyway, it's well known that when an time-varying electric field is applied to a material, the atoms, the molecules in there react to that electric field and try to oppose it. That's called polarization. Now, the different charged species in your material react at different frequencies and therefore different wavelengths to that electric field. If you're in the optical frequencies, you get color. Things get absorbed, things get emitted. If you go into the infrared, which is where your NIR heaters work, you start interacting with the vibrational modes of the molecules. So think of a molecule as lots of different masses in a spring. They start vibrating all over the place. Come down even further, you're into microwaves, and you get rotational modes. This is how your microwave oven works. Water molecules absorb the microwaves, and they start rotating. The friction of that rotating, banging into neighboring molecules, creates heat. Come down even further, and the radio frequencies that we're talking about here are so slow that nothing really happens at these higher frequencies unless you've got some ions in your liquid. And most of your inks will have ions in them somewhere. Then what happens is that the radio frequencies start moving the ions backwards and forwards. They collide into other molecules. The friction creates heat. That is dielectric heating. And it is completely different from the heating you get when you just pass a current through a wire. That's just normal Joule heating. That's not what we're talking about here. Now, what's really interesting is that here's water. If I was to have pure water, we'd have nothing happening at radio frequencies, and you get no heating. As soon as you get some ions in there, some salt, say, just common table salt, you start producing this effect that you can start getting some heating. There's an equation for you. I know most of you won't really worry about that, but the point is that dielectric heating in radio frequencies is really, really easy to create. All you need is some electrodes, the right material, and the decent electric field, and you're done. You don't need to make contact with the material you're heating. That's really important. So why am I talking about this? Well, the main thing is this. You can make some incredibly efficient heaters. 75% is possible. And that contrasts incredibly favorably with the 5% you might expect from hot air, or at best 10 to 15% from near infrared. Think about that as a user. Some of these corrugated printers, you can easily have 1/4 of a megawatt of heating on there. 1/4 of a megawatt running at 10, maybe 15% efficiency compared with this. The amount of energy you're saving is huge. It runs into an awful lot of euros. The other beauty about this is that, even though I'm a physicist and I understand how this works, it's almost like magic. If you don't have anything in the heater that's capable of conducting electricity, it doesn't get hot. So if you've got a non-conducting substrate like a plastic film or so on, it just sits there. It doesn't affect anything. So that's really great if you're trying to print onto a plastic film, for example, that would get hot under near infrared or hot air and could damage your substrate. The water droplets should be heated instantaneously all throughout the bulk. All your other heating techniques, they start from heating the outside, and the heat has to conduct inwards. So there's a dynamic effect there. This should be, and is, a very highly scalable process. You can have it running from watts, which is maybe all you need for a continuous inkjet application, all the way up to the kilowatts that you're going to need for corrugated and so on. Considerable freedom to design your electrodes. So you can easily conceive of ways in which you can do direct-to-object type printing. So it's a 3D system. It's best suited to flat films and paper and so on, but you can also do it onto 3D shapes. And lastly, and this is possibly even more significant for the commercial ideas, there's generally some scope for IP. So an interesting question that a few of you are probably still asking yourselves is, why, if this is so good, have we not seen it yet? And I think the answer to that is, you can't just make an RF heater, kind of build it and they will come. Because you've got to tune everything up to get the optimum effect. You've got to tune the ink formulation. You've got to tune the shape of the electrodes. You've got to tune the amplifier that you've got in there. And that means you're going to need a partnership to make it work properly. So this is kind of a model you can expect. 42 Technology, it's our company. We exist to develop technology. That's all we do. We're not selling a product. We're not market-facing. That's what a lot of you guys do. We just want to develop the tech. That's what we get out of bed for. You will also need an ink formulator. They're up here, very important. You need to, I think, design the ink to be optimized for this technique. But that shouldn't be a problem. That's what happens all the time. People design inks for UV, or they design their inks for other types of drying techniques. So there's nothing unusual there. You're a hardware vendor. You need someone who's going to build this machine and sell it. That's not us. And you're going to need some customers, ideally a lead one. And that's why I think this is actually quite a good forum to explain all this to you, because we've got all these people here. This is really quite exciting, I think, and potential to really change the industry for the good, because it's delivering something that the customers all want. So that's a quick snapshot of what I think is possible. We're all here standing and talking to each other about the change that's coming. Czar's Aquinox head has been released, and it's massively galvanized the industrial printing industry to look at these aqueous inks. We've had several talks from the likes of Madhu at ViraJet, and Cabot and so on, talking about the aqueous inks. It's good to make this all a reality. But there is the elephant in the room. It's drying, and this is the thesis I'm talking about. We've really got to start doing something about that. Because if you've got hundreds of kilowatts of heating going on, you're almost literally taking notes and burning them in front of the customer, and that's not going to be tolerated for very long. So I could talk about this for hours. You've got to go and get a drink, so I'll leave it with that. But I look forward to talking to you. Myself and my colleague Duncan are here. We've got a little stand over there. Please do come and say hello, and we can talk about this more some later. Thank you.